In terms of South Park comments, I thought I'd give a quick intro because I think most people in the audience are Bits and Bio guests. So SPC, as we call it, is a learning community for folks in the -1 to 0 phase of exploration. Hat tip to Jonathan in the back who coined that term for us. So we are a community of primarily technologists who are exploring what to do next. And TechBio is a huge area of focus for the community. We have a learning forum or 8-week deep dive into the space right now. And a real highlight of the forum is co-hosting this talk with Bits and Bio. But I would be remiss if I did not mention we have a founder fellowship program, which is a pre-seed program for people in -1 to 0 who are trying to start companies and would appreciate being in a cohort and getting lots of guidance. And the applications for that coincidentally close tomorrow. So I thought I'd mention it while you're all here. Just a pure coincidence. But otherwise, we're really honored to get to host this event and to learn more about what these 5 experts are going to share. So with that, I'll pass it to you, Nicholas.
Thanks, Mitra. So I'm Nicholas. Nice to meet those of you who I don't know. And Bits and Bio is a community building at the intersection of software and science. And so today I'm pretty excited for some lightning talks from various members of our community, diving into a little more technical detail about kind of some important systems in the biotech space. We've done this before in our Boston chapter, got some pretty good feedback, so we thought, can't let Boston one-up us. Let's do it in SF. And yeah, I'm excited to, have these as conversation starters for the mixer that happens afterwards. But Bits and Bio, we have a Slack community. We have kind of mostly organized virtually, but have in-person meetups on a regular basis. So if you're not a member of our Slack, please check us out. And with that, let's get to the lightning talks. Brian, I'll let everyone introduce themselves.
Hey everybody, I'm Brian Naughton. I'm a founder and CTO at Hexagon Bio. We're a tech bio company. We do a lot of synthetic biology, genomics, and we have a lot of automation. I'm going to talk a little bit about, let me check the time, LIMS and what I've sort of seen, and I'm going to structure it as like problems I've seen, and then I don't know if solutions is the right term, but other things we could think about doing to make LIMS work better. So first of all, what is a LIMS? I'm sure some of you know, but it's a little amorphous. It stands for Laboratory Information Management System, I think. And it basically means all the data that flows through the lab, input and output. So sort of like it can drive your lab in the most sort of extreme case, but it also could just be sort of inventory and stuff like that. The other thing we know about LIMS, apart from what it stands for, is that it sucks and everyone hates it, right? That's the thing everyone agrees upon. So why does it suck? I think it sucks because it's not a bits problem, right? Coding is like not easy, but it's not that hard. It's not an atoms problem. It's sort of like the two things together, and that's really where there's a lot of friction between those two surfaces. That's where you gotta be very aware of where things meet. So I would say the problem, as I'm defining it here, and sort of like I think the one takeaway from what I'm going to talk about is that I think it's not really a coding problem. So you see a lot of startups, LIMS startups, being like, here's the code that will solve your problem. But what I see very routinely over and over is that it's really a modeling problem. So like, what is how does this object in the real world relate to what's going into the database? When I pick it up and put it in the machine, what does that mean, right? This is not a coding problem. So how do you deal with that, right? There's no code I can sell you that will solve that problem. It'll never work. That's a big problem. And if I was looking at our sort of internal tools the other day, and we have 600 different actions currently that people can take. So, we put a plate from here to here. We want to log what happened. That's one of the 600 things. And I'm sure that's not unusual for sort of companies that are at our scale. So that sort of covers the problem, I guess, a little bit. But what are sort of potential solutions here? I think what we do at Hexagon is we have engineers solve the problem, right? So engineers are very good at modeling things. They don't do science necessarily, right? They don't understand necessarily what the protocol should be, but they can handle the problem of doing the modeling. The catch is that engineers are very expensive, and this is not necessarily like their expertise or even what they want to do. Model scientists, protocols. It's not like the dream of every software engineer. So it's a hard thing to hire for, and it's a hard thing to do right. And it sort of feels bad, right? It doesn't feel like the right way to do things long term because not every company can hire software engineers. Biotech shouldn't have to hire loads of software engineers. The other possible solution here, I think, is very unproven, but it's like getting your scientists to do it through some kind of no-code or low-code kind of thing. And I think people are trying that. I don't have a good sense of whether this will work. It seems like it would be very hard because I think there's a disconnect between how the scientists understand how the limbs work and how it actually works. And I think you would need to do a lot of education to get your scientists to actually be able to do the limbs thing. And the third option, which I think is not really an option, but something that I'm hoping the industry will sort of do more of, is just some more integrated systems. So at Hexagon, right, we do sequencing. We do all of our own robot programming for all of the library prep stuff from scratch. And we do it on these Hamilton machines that everyone has. And there are probably like 100 biotechs out there, or hundreds of biotechs doing sequencing basically the same way on basically the same machines. And everyone's inventing it from scratch. And that's a huge waste. And that means we have to model all of those things that are happening. But you can imagine a world, right, a beautiful world, where there's something more integrated where you just know about what's going in and what's coming out. And then you don't worry so much about how to model it and what's going on, right? You don't have to worry about it because someone's worried about it one time a lot and made that system work. So I don't think that really exists right now. I don't know how long it will take to get to that world, but something like that in combination with, I don't know, just better tools, I guess, should help improve limbs. That's all I got. Thank you.
So one thing you're pointing out is like better integration. Maybe someone can solve it once and then the rest of the industry doesn't worry about it. One thing I hear a lot is, oh, but our science is so special and custom and like solving it once could never work in our unique case. How do you think about kind of that as a broad problem?
Yeah, I think that is a huge problem. So part of the reason I picked sequencing is that I think sequencing is one of those cases where everyone does it the same way, basically. It's rare for a biotech to have some new take on sequencing. I think there are other things like, let's say cell lines, trying to like see if cell lines die or not, like that type of thing you could imagine encapsulating as well. So I guess my hope is that the surface area of the uniqueness of your biotech is not that great, right? And I think if companies thought about it sort of with a cold eye, you would see that most of what your biotech does is routine, and a few things are special, and there should be some kind of market solution, I think, for the routine things. I say should, right? That's the problem, right? It should work. It's just unclear to me how and when it will work.
We had a member who was at South Park Commons, and she went to this company called Benchling.
Yep.
And they claim to be the answer to all your limbs/automation. Yeah, it's a funny term, but can you tell us like what is Benchling in your experience? For us, it didn't work at my previous company, but
yeah, we had Benchling licenses. I think Benchling, for those who don't know it, it started as an electronic lab notebook, meaning sort of like a place to store your data with some tools, kind of like DNA tools like primer design and stuff like that, as I understand it. And then they sort of expanded into inventory management and then sort of expanded a little bit more into what you could call a LIMS. Certainly for our purposes, it was in no way what we needed. That's not really a slide on Benchling. It's just we were trying to run the lab through software, right? We wanted to operate the lab like a machine, like with software. And Benchling was really more like an interface for scientists to put data in, take data out. That's what I saw. So I don't know where Benchling is now. I'm sure they've developed more in the intervening years. But I think sort of fundamentally, it could not have been the solution for us. It just wasn't at all the right kind of tool. I think that's the problem, right? LIMS is such an amorphous term. I don't even know like what you mean when you say like benchling is a LIMS. It's certainly not what we needed.
So I'm curious, what are the biggest problems that you're thinking about now, in the sense of, I mean, if you could have like magic wand that just solves one of your problems completely in the way you want it, what would that be?
That's a hard question for me to answer, because I think we have put a lot of sort of work and money into this problem. So we have like a functional system. So from my perspective, it's more like an industry-wide problem, because I think, we started with this idea of like having a lot of software engineers and having them work all the time on basically building a LIMS, right? I don't know, hundreds of thousands of person hours, just of engineer hours working on this. And I just don't, from my perspective, I don't see how that can work for the industry. It just doesn't really make sense. So I don't have any sort of immediate needs for Hexagon right now, except, bringing things online is always a pain. Working with the robots is a pain. These are all like pain points. But I think the overarching thing is like LIMS as a concept, I feel like is really hard to scale. I don't know where we go from here. I just don't know. Thank you.
Hi, I'm Tim Dobbs. I am the CTO and a co-founder of a company called Biosphere. There's me, so, And at Biosphere, we build bioreactors. So if you're not familiar with the bioreactor, it's basically the tank where you grow the cells. And that could be any kind of cell to make any kind of thing, depends what you're doing. But you need a good tank for that. And that's what we're building. Today, though, I'm going to talk sort of pretty generally about automation and how we can make our automation better. And I think it's going to echo a lot of your sort of thoughts, because I suspect this is a pain point that we're all sort of feeling. And let's talk about how to make it better using shared context. So that's kind of my thesis. I think a lot of us in the room can sort of agree that biology is kind of cool, and we can probably build some good stuff with it, right? Any disagreements? Good. And the claim here is that, like, well, you need automation to really make it scale. So I put, solar punk utopia into DALL-E and got this cool image back. And if you want this, you need automation, because you need all of the robots and all of the ways to manage not just the complexity of bio, but also the scale. Like, if you want something that big, you're gonna need robots, you're gonna need building automation, so on and so forth. So cool, right? We're all like pretty smart people. We should just do it, right? And we'll have it done probably by, I don't know, next Tuesday or something. But obviously not. So why not? And the answer, really, among other things, is that automation really requires context. So this thing is probably pretty darn good at building cars, and I don't think I would have it run a gel for me. I think it would probably end up pretty messy and with shards of plastic everywhere. And so, like in a lot of engineering disciplines, and software included, like generally software, you have to build tools that work for your application. If you build the wrong tool, it doesn't really work. And that's extra true with automation for a couple of reasons I'll talk about now. One is that automation exists in the physical world. It's not just code. It's not just an abstract workflow, although it also is those things. It's also like a physical thing moving. And this is a 96 well SBS plate, 127 millimeters by 85 millimeters, the classic. We love it. And so I can set up a protocol to make my robot run that, and then I change suppliers, and for some horrible reason, they send me 120 millimeters by 88 millimeters. Everything is ruined. As a human being, I might get this and be like, yeah, it's fine. It's still 96 channels. But a robot is going to say protocol analysis failure, or whatever your flavor of robot spits out at you when it's unhappy with you, because the actual millimeters matter. It has to know where it moves. So the physical context of how your automation is doing its work ends up really mattering. Further, support is actually a super huge issue with automation. So this is a Eppendorf BioFlow 115 that we bought used at Biosphere. And the hardware is in great shape. And this is us tearing open the controls on the back because we were trying to get data off of it. And the thing that first off, yeah, Tim knows that like it's already hard to get data off these systems, but the manual was pretty clear about how this could work. And we thought, we can duct tape it together. And exactly. So this is us literally checking every single signal that came off of it on each pin to figure out what was going on with it. What we eventually found, and Eppendorf was game to help us actually, even though we didn't buy this directly from them. So it's not on them specifically, but we found out someone 15 years ago flipped 2 of the wires. And so the manual said something different than what was physically there. And that was originally built in. And so 15 years ago, maybe someone at Eppendorf would have the institutional knowledge to say, oh yeah, that batch had this little twist, but it's been a while and no one really cares anymore about this used piece of equipment. And so in automation, institutional knowledge has to spread across the physical space, the workflow space, and the hardware space. And so you have to have that context of how do you actually use this tool? And that can degrade really, really quickly if you don't have a good community of people telling you how to do this. Put another way, if the one guy who knows how to use this quits, you're screwed. So that's one of the other challenges. There's a lot more challenges, but I won't get into all of them because it is a lightning talk. Essentially what this all builds up to, and it's exactly what you said, is that we just keep building the same tools over and over again. If the context changes even slightly, we don't have enough information to know how to make that little tweak, so we just build it again. We build another limb system. And we do it over and over, and the entire industry is this robot man walking on an infinity loop, and that sucks. So I'm not going to stop there because I obviously have an opinion about how it could get better. It'd be weird, right? If I was just all right, anyway, everything's screwed. I'll see you later. And my opinion is essentially when you build your tools, you have to build the contextualization in. And that's how we're going to get all the cool stuff we want. And I know Tim will appreciate this too because documentation is such a big part of it. And so build your automation tool and then also contextualize it. Say what it was used for, how to use it. And so if we got our robot and he has no idea what's going on, he walks around in a circle, but by adding the context to our automation tools, we can pull him out of there and look, now he's on this beautiful staircase with documentation and technical drawings and support from open source is actually really good at building robust support communities. And now he can actually build another tool on top of that, which is great. And look how happy he is. So cool. It's one thing to just say context document. Everyone knows that, right? Thanks. And I started to list out, there's actually lots of ways we can talk about contextualization. It can mean a lot of things, and I have a lot of opinions. I started to list them out, and then my girlfriend walked past me as I was making these, and she said, quote, "That looks really boring." So I will tell you more about that afterwards at the mixer, but I'm just going to give you one sort of trick and encourage you to take, if you take nothing else from this, which is publish your automation work. So pure software people know this. There's a good community of this. Automation, not really. But stick your documentation, your technical drawings, your code, toss that up on GitHub. That's a good thing to do. But Tim, you say, I work for a company. We don't really have an open source ethos. That's not really how it goes. And I say, yes, that's true. In a perfect world, I would love to just say, everyone just I'll be, the automation flower children and keep everything out. But you can't always do that. Instead, I suggest that you focus on projects that are very useful, but don't focus on the core IP of your company. If you have a company that makes proteins and you have to do sample prep with an automated robot for that, it's not core to run the sample prep robot. That's a good thing. Others could use that. What does everyone wins mean? Well, it's pretty broad. OpenTron's basically said, we're going to open source our entire robot firmware. And on the other end of that, this is a 3D printing model that lets you put a Petri plate on a robot, which is kind of nice. That's from iGEM Marburg. And so I encourage anyone who's thinking about their automation work to think about where they sit in this and what of their program or what of their projects actually could fit in this publishing space. So yeah, bring it back to your organizations, push for this, try to bring it into the community. You win because you get reputation, you get more feedback on your work, your project gets better. Your company actually wins because this, when people see that you're publishing this cool work, they'll be like, I want to work with that company. I want to work with that cool dude or lady who put that cool stuff together. And so you get better people in. And of course, the whole field of biology wins because this is the way we can build that staircase that helps us grow more and more and build the bricks that eventually become that solar punk city that I mentioned earlier. Cool, that was a lot. I obviously have tons of opinions about this. Come talk to me. If you want to see more, my open source repos, just go to bioart.org. That's my project where we make cool drawings, and there's a bunch of open source stuff that you can follow there. And then at Biosphere, we build bioreactors, and if any of this sounded interesting and cool to you, come talk to me. We're hiring. We're looking for software people, fermentation people. So I'm Tim at Biosphere.io. I'm on Mastodon and Twitter. Thanks. I don't know if there's any questions or, yeah.
On the comment about publishing your work, how easy do you think it is to publish it and then for someone else to take it and actually use it without having to modify it a lot?
Yeah. So anyone who's kind of published open source knows that it's not trivial. You don't just put the code up and say like, aha, now you may use it. In fact, there's a ton of maintenance, support, that kind of work. I think there's a lot of good examples of people who've done it well. It doesn't have to be a ton of work, but it's probably a little more work. But I think as a start, like I don't want to discourage people from just publishing anything. So just like if there's something to root around in. So yeah, it's a little bit of work, but we should start somewhere.
Great. I'm Josh. I'm presently at a company called Octant doing drug discovery. We're trying to build a biochem compute platform to sort of accelerate and scale drug discovery. I was previously at a diagnostics company called Invitae for about 10 years. I was the head of bioinformatics there through a lot of growth. I'm going to talk a little bit about bioinformatic workflows. I actually don't consider myself an authority or maybe even an expert on bioinformatic workflows, but I have the benefit of having made a lot of mistakes. And so I would like to, maybe share some of my learnings with all of you, and hopefully that will be helpful as you go forward. So maybe as a quick level set, right? Maybe everyone can raise their hand if they're familiar with bioinformatic workflows. Okay, many of you, not all of you. Do a quick level set. So what is a bioinformatic workflow? Essentially, it's a way of taking data from a source, putting it through a bunch of processing steps, and then coming out with data at the end. So oftentimes this looks like raw instrument data at the beginning, and it looks like processed results, maybe variants, maybe some other interesting summary of that data at the end. And this is kind of a typical bioinformatic workflow. This is a toy example. Don't go implement this. But you can see that essentially it's a whole bunch of steps that are arranged and that are doing different things, that are processing sort of raw instrument data, in this case raw sequencing data, all the way up through variant calls there at the end. So again, not just kind of a toy example. And what I want to sort of say about this is that there's a few characteristics of bioinformatic workflows that are important. One, they're sort of highly nonlinear directed acyclic graphs. So directed acyclic graphs is just sort of a mathy way of saying that there's a lot of splits and joins going on as you look at this bioinformatic workflow. Because of that, there's a lot of opportunities for kind of naive parallelization. So you can see that sort of the dependency structure of this is such that you can run a lot of steps at the same time. So that's one way you can parallelize things. There's also a lot of parallelization possible just by virtue of being able to sort of chunk work. So you might do something, you might do like your SNV and indel calling by chromosome, for example, and you might do it independently by chromosome and then join all of those results at the end. So lots of parallelization possible. And then finally, like they tend to be quite compute intensive. So typically we're talking about frequently we're talking about tens or hundreds of core hours per step. We're talking about large amounts of RAM. We're talking about lots of compute intensive stuff in some cases. So because of that, there's a lot of desirable properties. Of course, you want them to be computationally scalable. You want to take advantage of all that parallelism that's in there. You need them to be reproducible. When you have some data at the end, you want to be able to answer the question, how did I get this data? What steps did I run? What versions of software? You want to be able to save and reuse your work. You want to be able to, if something fails, you want to start from a midpoint, not go all the way back to the beginning. Or maybe you're running something completely different and you've already done part of the work and you'd like to reuse that. You'd like to reuse components and even sub-workflows out of this. And lastly, you want to be able to rapidly develop and iterate on your ideas in a bioinformatic workflow like this. So this is kind of the setup for what is a bioinformatic workflow, why is it important? So again, this is the 10 commandment, or the 4 commandments of bioinformatic workflows. And this is the first one. Thou shalt not write thine own workflow manager. So here's your obligatory XKCD. The very astute among you might notice that there are actually 14 workflow managers listed on this slide, just like there's 14 in the XKCD cartoon. Is that a coincidence? No. There's actually many, many more workflow managers than this. This is just a sampling of 14, relatively popular ones. So there's lots of these, and yet I've seen many people sort of write their own, and I think there's two reasons for that. One of the reasons might be that they look at this field of workflow managers and they're like, but it doesn't do exactly what I want, so I'm going to write my own. Or they might look at this field of workflow managers and say, you know what, it just seems so complex. The learning curve is just so high to use these. I think I'm just going to do something simple. I'm going to write my own. Listen, I don't think it's a good idea. I think that chances are that whatever company you're at, unless you're working at one of the companies that makes these workflow managers, that's not the area of expertise that you want to cultivate at your company. And so it's probably not a good use of time. Corollary, don't use GNU Make as your workflow manager. It maybe gives you like good geek cred or something, but I don't think it's a good idea. There's far better options that have far better properties and learning curves that are better than Make, frankly. Sorry if I offended anybody. This is a lightning talk, so it's allowed to be a little inflammatory, right? Okay, thou shalt run thy workflows in the cloud. This seems really obvious, probably to most people in this group. I think that it's probably a little different when you join a small company and there's like a server over in the corner that's like from somebody's academic lab, and they're like, it would be really easy to get started on this server. We can just start running things there. And later we'll do the work and we'll move to the cloud and we'll make it all modern and everything. The problem, and I think many of you are probably familiar with this, is that whatever solution you choose starts to grow really deep roots. So you start to rely on elements of that initial infrastructure, of that computer in the closet that you're using. Your consumers will start to rely on the file system. You'll keep reference data there in a way that's not ideal, and you'll do a lot of things out of convenience. And you'll just keep growing these deeper and deeper roots, and there'll be this vicious cycle where it just gets harder and harder and harder to get off of this solution. I think this is one of those things where it takes a little bit of extra time and capital up front to do this, and it pays dividends over time. So there's a lot of cloud solutions. I'd say if you have 5 or 10 engineers at your disposal, like great, go ahead and roll your own cloud solution. But these things are actually largely, this is not an exhaustive list, and I don't have like clear recommendations about which of these to use, but like these things are kind of plug and play. You can use these and they do a lot of the heavy lifting of the software and cloud infrastructure for you. So it's pretty easy to get started on these. 2 minutes left, perfect. 3, thou shalt separate integration and workflow. So you're definitely gonna have, or you're probably in your informatic workflows gonna have to integrate with other systems, LIMS, variant databases, etc. You could do something ad hoc and talk to all of them in the different steps as you're going through. I would highly recommend that you think about layering things just like you would layer any software system, and doing that integration upfront and at the end of your bioinformatic workflow. That way your bioinformatic workflows can stay just as pure computational workflows, and they don't, you can reuse the components, you can test the components. It makes everything kind of easier, just like you'd layer any other software. I'm gonna try to hurry here. 4, thou shalt separate what and how. This is a little more sophisticated, little more subtle, but essentially the idea is you want to separate things out between what and how. So you have kind of containerized tools, you have a workflow specification, and that tells you everything about what you're doing. So that workflow specification is going to tell you about what tools you're running, what versions of the tools, maybe even a little bit about what the requirements of those tools are computationally. So you specify all of that, and then on the other side, you have an execution engine that takes that workflow and can run it in a multitude of different ways. So maybe you want to run it on AWS, maybe you want to run it on your local computer for testing. There's lots of ways you can run it, and there's lots of things that this helps. Notably, it really simplifies the implementation and allows you to specify the workflow and really focus on that, and not maintain like a horrendous series of conditional branches about where you're running. It also makes it really nice to generate static analysis documentation of your workflow. Lastly, and this is kind of a small bonus, sorry, I might be going a little over here. Am I, Nicholas? Am I okay? All right. This I think is really in keeping with what we've talked about, but this is kind of collaboration models. I talked to a lot of people, and at a lot of companies, the collaboration model between bioinformatics and engineering is what I call the over-the-wall model, where the bioinformaticians think really hard about analysis and algorithms, and they write them up in like R or Perl or Mathematica or something. Then they toss them over a wall, and they say, here, engineers, go implement that. And the engineers are responsible for doing all the rest of it. And I think the problem is that then the final product, there's not really any ownership, because nobody feels ownership over what's been built, and it's challenging. And so I really encourage all of you and everyone to think about more of a meet in the middle model. The workflow is kind of the place where you'd like to meet. So the bioinformaticians work on the analysis and algorithms and put them into the actual workflow that is like the production workflow. It's the real one. And they focus on that part. And then the engineering folks focus on what I would call platformization, right? Making that workflow really nice and easy for the bioinformaticians to develop on, and also scalable so that it runs really well and can run in a variety of circumstances. I would love to talk more about this with y'all afterwards. I think I'm out of time now, but I think this is a really great model for collaboration. It's a little bit organizationally complex relative to the first one, but I think if you can, my experience has been that if you can navigate that complexity, it actually works really well. That's all for me. Thanks. Do we have time for questions? One question.
This was amazing, by the way. I would love to see like a blog post or something written about this. Super valuable. I'm curious, for your time at Octant, what solutions have you chosen out of the ones that you presented, and why?
Yeah, so I would say like the problems at Octant are a little bit different than some of the ones I described here. We're a much smaller company, so we're definitely kind of meet in the middle. We are in this modality right now, to be completely honest. We're working towards, and Nicholas knows this all too well, we're working towards a solution where we're using Dagster. Yeah. That's not super strongly held by me, by the way, so I'm not endorsing him. But that's a factual answer to your question. Okay, thank you.
Well, hi everyone, I'm Tim. I am the final speaker, so if you want to stuff your face with empanadas later, you only have 10 minutes left. Make it with me here. And so I'm here to talk about Polymerase, which is a project that started during the pandemic with a good friend of mine, and I call it the missing software package for engineering organisms, or synthetic biology in general. And I like to joke that I'm somewhat of a mad biologist myself, and I originally thought this talk was me pitching goofy GMO ideas to VCs, because that's literally what Nick pitched this talk to me as. You lied to me. And so I was originally going to tell you all about why I want to make flying seaweed and how cool it is, and just get really into that. But instead, we got to talk about GenBank. All right. So as you'll see here from the SpongeBob meme, a lot of people say SynBio software is not that bad, except for these speakers who are quite intelligent and great and know what's going on. But then you look at GenBank, which is this antiquated, like, for the developers here that don't know biology, it's like, imagine if GitHub was made in 1978 for genomes, and it was made by the government, and they didn't ship JSON, or even XML, or even ASN, which you probably never heard of. They shipped GenBank. And GenBank is this white space-based format. I'll tell you more about this later because I hate this format with more passion than a person reasonably should. But when you get into reading the literature, you start finding stuff like code available upon request, abandonware. There's no unit testing or documentation. There's always the classic, it runs on my machine, and the mountain of spaghetti code. And this is kind of what we're working with in a lot of cases. And it's so bad that some people get really mad about it and leave the field entirely. This is from 2012, so this is not an old problem. This is not an old problem at all. People have been getting, so this is what you're working with if you get into the field, by the way. It's like, listen to this guy. He's not wrong, okay? And so I'm not gonna say the line right here out loud because I don't know how kosher that is for this talk in this venue. But people are mad about the quality of software in the field. And it's changed a little bit. It's gotten a little bit better, but it needs to go faster. And so that's why I wrote this package. It's called Polymerase, short for a enzyme that copies DNA, and it does fairly basic things, in my opinion. But it has high unit coverage, high unit testing. It's fast, scalable, and currently offers almost everything you need to do synthetic biology beyond like metabolic engineering stuff, which is a little bit more in depth than what you can do with a standard Go library. And so this is the stuff we're shipping like as of yesterday. We're adding RNA and DNA folding like tomorrow. A nice Italian man is adding this. So this is an open source project. It's all MIT licensed. You use it at your company. And we do alignment. We do basic cloning. Golden Gate. Gibson's coming out soon. IO for FASTA, GenBank, GFF, PolyJSON, which is no one ships JSON in biotech. So I just do that for myself. I shouldn't be making the standard here, but I am. And then there's a nice enzyme database of cut sites from NEB that we parse, and Uniprot, which is the data model for proteins the kind of proteins that Chloe was just talking about. We do primer design, so think like COVID tests, small little pieces of DNA that go between two sites that you want to copy and see if there's a lot of. Then basic stuff like you'll find if you get into bioinformatics from the tech side, which is what I originally wrote this talk for. Well, originally I wrote this talk to pitch flying CV monsters to VCs. But when I rewrote this talk, one of the things you'll find with biotech is there's these little quirks about the data. Where you're not working with just regular strings, you're working with strings with context. Like Tim mentioned earlier, there's a lot of context here that you have to be aware of. And so you can't just, one simply does not compare two DNA sequences and say they're not equal if they're not equal as strings. You have to align them. You have to look at them and see if they actually compare. And there's little ways of doing this where it makes sense biologically, but logically and from a computer science perspective, it doesn't. And so Poly kind of just abstracts a lot of that for you and kind of bakes in the details. And we also, this is the stuff where like we do better than anyone else. Codon optimization, DNA synthesis fixing. Our DNA synthesis fixer is like literally 1,000 times faster than the next open source package, which I find kind of wild, but Keone whipped it up in a weekend, and who am I to argue? And so this is just literally what it looks like. It's just, we put the context in the code. It'll tell you, oh, you can't read that from distance at all. But essentially what we do is we put biological context next to our code, so we can tell you what everything is doing and why we're doing it that way. And sometimes I literally have to say, hey, this data format is effed because the NIH says it has to be effed. I have no decision in the matter here. That's just how it has to be. And so the way this whole project even got started is I got a call from Keone. He's not here tonight, but he shows up occasionally. He's a major contributor to my project. And he was at Drew Endy's lab at Stanford, big synthetic biology lab. He may have even come up with the term synthetic biology, like he may have named the field. And I get a call from Keone at the beginning of the pandemic where he was quitting his job at Dendy's lab, moving back with his parents, because that's actually a pretty smart move during the pandemic. I wish I did that, and I'm a little old for that. And he had to convert JSON to GenBank and back. It's a very simple problem, right? JSON, as we all know, is the world's most common data interchange format, and GenBank, as I've described to you, is this nightmare of a data format decided on by scientists in the deserts of New Mexico in 1978, and we literally don't know who came up with it. I can't find someone to blame. There's no get blame for this. It's obnoxious. So he says, there's no way to convert from GenBank to JSON back. And my BioPython script keeps breaking. I was like, what? So I was concerned, and I was, I had some free time on my hands, so I wrote one, and it took me 2 freaking weeks to write this parser. And it's not like I've never written a parser before. I've scraped whole websites before. It's not that hard. 2 minutes? All right, let's move then. So here's the parser. It works great. It's been rewritten 1,000 times. Wait, can no one do synthetic biology because no one can parse GenBank? And the answer is, what the fuck? Sorry. So I began a bit more. Everything is super well tested with 90% test coverage, beginning assembling gang of random internet nerds. And I gotta tell you, random internet nerds are goated. They're really good at getting stuff done. We've accomplished more than a lot of symbiotic startups in the space. And literally my RNA folding was just written by this lovely Italian man the other day. No affiliation with me, just oh, you're cool. I'll do this for you. And so again, here's the package for it. Here is a nice little example of, if you want to clone out every single coding region of B sub, which is the bacteria that's used to produce natto. It's it feeds on soybeans. You can literally read in B sub from its GBK that you can get from GenBank. You can go through every feature on there, look at the CDS, if it has a CDS type, and then for every CDS, just say, hey, can you give me the sequence and design forward and reverse primers for that? And can you do that 4,000 times within a second? And then it's done. And it's one of the many features we have. And I am now moving from this pretty solid framework that is 90% done to new things with a company I guess I am announcing tonight called Bepop.Bio. Go to the website, please hire me. and talk to Esther, who's in the back, I think still. Yo, raise your hand. Yo, what's up, Esther? She is much better at sales and is not an anxious wreck in front of people like I am. So, yeah, that's my talk. Any questions? I didn't get to drink this the whole time I was bringing them up here.
Why'd you choose Go, and what do you like about it, and what do you hate about it?
Because it's 25 times faster than Python. It's easier to develop in. All my stuff can run pretty much anywhere. And you know how many developers just write it because it's Go? Like all of them. I get so many like very professional Go devs just showing up because they want to work in the language and they're tired of looking at Python scripts. I'm not even kidding. One guy literally came to me and was like, "You're the only biotech person I've seen who writes software like it's this century. Everything else is Java if it's enterprise." And I was like, "Dang, dude." So that's why I chose Go. And it was a decision where I needed to do something where I was thinking about separating a command line tool like all scientists try to do, which I eventually decided not to because it's too much of a hassle personally. But I wanted something that would compile and that was statically typed. And that came down to Go and Rust. And like, I played with Rust a little bit, and Rust, you're just shaking your head like, no, Rust, no.
Oh, and Rust is great. It's just we won't find other developers as easily.
Okay, well, they're having a moment right now, but like my experience with it is like everything's great except for string manipulation, and it's just like, it's a hassle. You have to learn it. It has its own own system for it. But maybe it's gotten better since the 4 years I last checked it out. So that's why I chose Go. Also, it'll save literally 25x on your Amazon compute bill if you're making a lot of primers. I don't think you're making that many though.
I think that's it. Thank you, everyone. These were great talks. Really enjoyed it.